Hello, welcome to class. So, today we're going to be doing dependent and independent events featuring two-step equations. So we're going to be moving away from Venn diagrams and two-way tables to kind of actually explore the probability of things happening, how to understand that, how to calculate it, and what dependent and independent mean. So, what you will need for the lesson, if you haven't already got it, is a pen, a book to take notes in, and a calculator. If you don't have that, pause it and get that now. So, moving on, the very first thing that we need to understand is that our probability of something happening is equal to the number of desired events over the total number of events, or the sample space. This is a really important piece of information. Okay, now this is just like, your contextual knowledge, the thing that you need to know first before we step into the learning. So, understanding dependent and independent events. The way that we're going to do this is through kind of representing it in a game. So let's maybe use this. Let's say we have one, two, three, four pink balls. We have four green balls. So in this, the first game that we're going to play is we pick two balls with replacement. So what that means is if I take a pink ball, then before I take the green ball, I need to add my pink ball back. Okay, so we can understand this bit better using what's called a tree diagram. So one of our first two options, right? If I pick a ball, I can either pick a pink ball or a pink ball or a green ball, right? Now, if I have four of each, what is the chance that I pick a pink ball? Well, that's where we go up to the thing before, where our probability is the total number of, like, our desired events over the total number of events. So we have four pink balls, which is the desired one, over the total number, which is 8. 4 over 8. Now, we can simplify this down to 1 over 2. It is the same for the green balls, right? Half and half. Now, I'm just going to maybe erase this bit here and move this bit just over here, right? This is normally how a two-way table is represented, right? In this section here, this bit here, that is your probability. That's where you represent the probability of something happening. And then this section here is the event. So what we're actually looking at happening. Okay. Now, the most important thing, or one of the most important things that happens is what would be the chance that I pick either a pink or a green ball, right? Now, if we look at that, we need to add these two probabilities here. We need to add pink and we need to add green. So intuitively, we can understand that if I'm either picking green or I'm picking, sorry, pink or I'm picking green, that's almost as a certain outcome that is going to happen. And we can see that by adding half plus a half. So if I wanted to know what the probability of these two events are, we add them together, half plus a half. So that means I'm either picking pink or green. Half plus a half is a whole. And one of the things that you see when you're looking at tree diagrams is that the probability of either one of these branches, the addition of those two branches, needs to always equal 1, right? And we'll see that a bit further down the line as well, okay? Okay, so we'll go back to our initial question. We picked 2 balls with a replacement. So now we're going to move into 2 other options. Go back to my pen. And we're either going to pick a green ball or we're going to pick a pink ball. Now, because we've put them back, we've taken a ball and we've put it back, the probability of picking another pink ball is half, same as picking a green ball. Half, same as picking a pink ball, and same as picking a green ball. So here are our outcomes. We can either pick 2 pinks, a pink and a green and a pink, or a green and a green. Now, initially, I want you to notice that if we add these two, the 2 branches of that initial stem, this stem here, then we will get 1. Half and a half is 1. So the other cool thing to notice, the way that we calculate the probability of pink and pink, if we want to know what our final outcome is, we need to multiply along the chain. So we have half, we look at what is the probability of getting pink? Probability of getting our first pink. Maybe I'll use there. And then we need to go along. So we've gone through here, we've landed here. Now I need to say, okay, what's my probability of getting this pink? That's also a half. So I need to go up the chain, multiplying each time. So these 2 probabilities we move across. It's equal to half times a half, which is a quarter. Now, if I want to know what the probability of getting pink first and then green, so probably pink, go up, okay, I need a half, and now I'm going down here, which means I need another half. So I'll just quickly write this in. Is equal to a half times a half again, which is a quarter. Okay. Now we can do this for all of these where we're going green and pink. Okay, probability of getting a green first is half. Multiply that by the probability of getting a pink. It's another half. So we can say that's a quarter. We know that this is also a quarter. Now, this is cool because you can also see, right? We have 1, 2, 3, 4 different outcomes. Okay. We have, I'll even make a highlight. We have 1, 2, 3, 4 outcomes, right? 4 outcomes. If I wanted to look at this one specifically, I have 1 of my 4 outcomes. So it's represented there as well. Okay. We have 4 final products. So this is here the sample space. And this here is our event. We have 1 of these, which is the green and green. We only have 1 of those. And then we have 4 events. We have 1 over 4. But you can see that in multiple different ways. A lot of the times you can just think about probability intuitively, where you can be like, oh, okay, I've got 4 different things. I'm looking at 1 of them. So the probability of that happening is 1 over 4. But you can also prove that using this. Now, what we've just looked at is at the independent events. And the reason you can see that is because I can say that picking a pink this time or a green this time has nothing to do with my first suggestion. Okay, and this here is where I might even just make this a little bit smaller before we get into it. Okay. All right, so we'll move over here. This is where we kind of come to understand what our dependent event is, right? Oh, sorry, independent event. Now, we can see I can either pick a green or a pink ball, okay, in my first one. Now, because, in fact, actually, I can pick out of the 4 greens and the 4 pinks in my first pick. Now, sorry about that. In my second, because I'm putting them back, I'm still picking out of either 4 pink greens or 4 pinks, right? And so you can intuitively understand my first pick has nothing to do with my second pick, right? It's like if I tossed a coin, if I flipped a coin, I can either get heads or tails. Does that outcome affect the outcome of my second flip? No, no, it doesn't. Not at all. It has nothing to do with it. In either of these picks, I have a 50-50 chance of getting pink or green. Okay, so these are independent events. And the way that you prove that is you can say probability of getting pink and a green is equal to the probability of getting a pink times the probability of getting a green. So what does this bit here mean? Well, this is saying I've gotten a pink and a green, right? Now remember, this little sign in here means and. And when we're talking about it in terms of two-step equations, it is representing where both happen. So here I'm looking at pink and green. So pink and green here. Okay. Now, we calculated it before. The probability of pink and green, in fact, go over here. We know that the probability of pink and green is a quarter because we knew we can say this. Probability of pink and green is equal to the probability, or it means the probability of getting 2 greens. Sorry, it means probability of getting pink then green, right? Here, which we said is a quarter because if I get pink and then green, I have a half a chance first and then another half a chance second. We multiplied those across, which is what we did right over here. Okay, pink, then green is a pink, then green. I'll use my highlighter maybe. Pink, then green is equal to a half times a half, which is equal to a quarter. Okay, so we can say here probability of pink and green is the same as saying probability of pink then green, which is, we know, a quarter, right? But over here, is this equal to probability of pink, which is a half, times the probability of getting green, which is another half, okay? And a half times a half is a quarter, and so that is a way that you can show that it is independent, okay? Now, the important part here in your notes, which I want you to take down, is this. Let's just make this a bit smaller first. All right, so here is a little formula that I want you to put in your book, okay? Formula that you kind of need to prove some stuff. But basically, it says for independent events, we know that the probability of one happening and then another happening is the same as the probability of one times the probability of another, right? And that's just a logical thing that we've talked about. You can see that you follow your Venn diagram, like your tree diagram, and this happens. And that's why we have this, okay? You're following your tree diagram, you're doing one and then it doesn't change, and so then you do the other, okay? Now, for dependent events, this is not true, but we'll get into dependent events next week because that's called, conditional probability. For now, we're only really going to be looking at independent events, and then we're going to be looking at dependent events without really going into the formula and that explanation. But we are going to look at them. Okay. Now, the other thing that we're going to look at here is my second option. I have 4 green balls. 4 green balls, 4 pink balls. Now, what I do is I pick 2 balls without replacement. Now, before I even go into it, right, let's have a think. If I take a green ball, or let's say, I'm choosing my first ball. It can either be pink or it can be green, and there's a 50-50 chance because we have 4 of each. If I take a green ball and I keep that green ball, now I'm going to take my second ball. Which one has a more likely event, like chance of happening, pink or green? Now, hopefully, we all said pink, right? And we can kind of intuitively understand that because we've already taken a green ball. So now we have more pink balls left. So we're more likely to choose one of them. And that's why this is called a dependent event, because the outcome of the first thing happens directly affects what the outcomes or the probabilities or the likelihood of something else happening next. Okay. And we can show that using a tree diagram, right? Over here. So we have pink, green. Then we have whoop, pink, green. And over here, we also have pink and green. So let's have a look at this. In my first selection, I have 4 pinks and I have 4 greens. So my probability of choosing a pink is 4/8. Now, I'm going to leave this in this format. We could simplify it down to a half, but just for this purposes, I'm going to leave it as 4/8. And it is the same as choosing this one. Now, I've chosen one now. I've chosen one. So what's the probability if I choose a pink? Let's go down this route here. I've chosen a pink. Now I'm looking at what the probability of me choosing a green is. I've taken a pink. I still have 4 green balls. So I can say this is 4, right? How many total balls do I have? If I've already taken a pink, right, we can look at that. I've already taken a pink. So now I have 3 and I have 4. So I have a total of 7. If I've already taken a pink, we can look at this one now. That means I only have 3 pinks left. So the probability of me choosing another pink is 3/7, right? Does that make a bit of sense? Hopefully. So the same is said down here. If I have taken a green, what is the probability of me choosing another green? Right? Well, I know that I've already taken some, so my total number is going to be down by 1, down by 7. Now, I had 4. Let's see if I can. Right, here we go. Here we go. Beauty. So I had 4. I've taken 1, and now that means I have 4 greens, 3 greens and 4 pinks. So I only have 3 greens. Same as said here. I have 4 pinks out of 7, right? And that you can see the probability changes from the first event to the second event. Changes. You can see the probability of choosing a pink the first time is 4/8, then choosing another pink the second time is 3/7. So the second outcome is dependent on the first outcome, right? So we can show that, you know, we can say using our formula, this won't work, right? Because we have here, let's see, pink and green, pink and pink, green and pink, green and green. Now let's just look at this one for now, okay? What is the probability of pink and green happening? Well, it is the probability of your first little bit. So we're going to follow the tree. It's probability of 4 over 8 times the second thing happening here, which is 4 over 7. And that is equal to 16 over 56. 16 over, well, let's just keep it as that for now. I don't have my calculator on hand, and so I can't figure that out fully. But it would simplify down because they're both even, and so then you could get it into 8 over 20, 28. And I think you go again, so 4 over 14, and then again into 2 over 7. And that's where I would finish. All right, I might even just do that. 2 over 7. Anyway, so here, let's try that in our formula, right? So the probability of pink and green must equal the probability of pink times the probability of green for them to be independent. We know that this is probability of pink and green. We just calculated it over here. So that's 2 over 7 is equal to the probability of pink. Now, we're looking at the first thing. Here is the probability of pink initially. We're going to look at the initial ones. So here, this is the probability of pink. This is the probability of green. Now, what these are, we're not going to name these for now, but this is actually not the probability of pink. What this is called, in fact, we'll front load. This is the probability of pink, then green. Sorry, green, then pink. Sorry. Yeah, pink, then green. Pink, then green. It looks a little bit different, so we're not going to use that. Anyway, just that's kind of what we're going to be looking at next week. So, yeah, probability of pink is 2 out of 4. And probability of green, sorry, 4 out of 8. The probability of green was also 4 out of 8, which is a quarter. And these are not the same, so therefore they are not independent. Or you could say they are dependent. Beautiful. All right. Now it's pretty self like this stuff flows nicely because all you got to do really is build your tree diagrams and follow them and understand how you can take information out of that. Right. I'm only going to do a couple examples because I don't know if we need to spend heaps of time here. I would prefer that you guys, practiced and got it done. All right. The first example I'm going to do is this. A number game uses a basket with 10 balls labeled from numbers 1 to 10. One ball is drawn at random, then another ball is drawn at random. What is the probability that a ball labeled 2 is picked once if the balls are drawn with replacement? Then, what is the probability that the ball labeled 2 is picked once if the balls are drawn without replacement? All right. So, how do you lay this out? The first thing that we want to be doing is we're going to be looking at the probability of a 2 being picked, and conversely, we're going to be looking at the probability of not picking a 2, which is this little thing here. So our tree diagram will follow, right? It is going to be, let's do A first, okay? So A. Let's draw our tree diagram. We're going to be picking either 2 or we're not going to pick 2. And then again, we're going to pick 2 or we're not going to pick 2. Same for here, right? Now, the first thing we're looking at is it is with replacement, which means we're putting it back each time. Now, we have balls 1 to 10, okay? So, shall we just... Now, really, I'm only going to mark 2 here, okay? That's all we're going to care about. Now, 2, picking a 2 is 1 out of 10. We have a 1 in 10 chance because we have 1 out of our entire group, 10. So we know two things. The probability of me picking 2 is 1 out of 10. Then probability of me picking 2 plus this must equal 1. And so the only thing we can, like, you can, deduce this either intuitively or you can prove it. So we know that the probability of not picking a 2 is 9 out of 10. Now we can show that here because probability of picking not to is all of these in this out of 10, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 10. And we also know that 1 out of 10 plus 9 out of 10 is equal to 1. Now, because we are not changing and we're putting it back, the same likelihood is again, right? Probability of picking a 2 the second time is still 1 out of 10 because we've put it back. And this is still going to be 9 out of 10. This is still going to be 1 out of 10. And this is still going to be 9 out of 10. So the question asks, what's the probability of picking 1, 2? Right? So we need to total this, right? We're going to have a look. Here, we're going to say this is the probability of 2 and 2. This is the probability of 2 and not 2. This is the probability of not 2 and then 2. And then this is the probability of not 2 and not 2. All right. Now, we need to see how many of these include at least 1, 2. Well, we're looking at, in specifically the 2. We're not looking at the not 2s. We're looking at how many include a 2. So this one has them. This one has 1. This one has 1. This doesn't have any. Okay. So we need to find the probabilities of all these three things. So let's have a look. We're going to use it, follow the tree diagram. I'll do it in pink. So here we have 10, and then we have, 1 out of 10, and we have another 1 out of 10. So we have 1 out of 10, and we're going to multiply it because we're going to follow the tree by another 1 out of 10, which is equal to 1 out of 100. So small chance, right? Now, this one here, maybe we'll do it in green. We have 1 out of 10. We're going to follow that. And then we have here 9 out of 10. So we have 1 out of 10 times by 9 out of 10, which is equal to 9 out of 100. So for those of you who might need a refresher in multiplying fractions, the way we multiply fractions is we multiply across this way, right? Anyway, we'll move into the next one. Same thing, right? Let's go again. We're going to do the probability of not to followed by 2. So then we have follow the tree diagram. Probability of 9 out of 10 multiplied by, let's go this way, the probability of 2, 1 out of 10, which again is 9 out of 100. Here. Let's do this one. Final one. We know that we're going to follow the tree diagram. So the probability of not to is 9 out of 10 times the probability of another 9 out of 10. Which is 9 nines are 81. Fantastic. Out of 100. Now check this out, right? What is 1 plus 9 plus 9 plus 81? Let's just do it quickly. 1 plus 9 plus 9 plus 81. This is 10. This is 90. So the addition is 100. So we can see that in all of these cases, the total amount of outcomes is 100. So we will have 100 of 100 chance of at least one of these things happening, right? Now, here, we're not actually looking at this. The question is, what is the probability of picking at least 1, 2? So this has a 2, this has a 2, and this has a 2. So we are going to add those together. So we can say the probability of picking 1, 2 is equal to the probability of a 2 and then a not 2 plus the probability of a 2 and a 2 plus the probability of the not 2 and the 2, which is equal to, when we grab those pieces of information from over there, we can say that this one, we remember, was 9 out of 100. This one was 1 out of 100. And this one was also 9 out of 100. So 9 plus 1 is 10, plus another 9 is 19 out of 100. So that is our final answer. Probability of getting 1, 2 is 19 out of 100. All right. Now, let's also do the second question. What is the probability that the ball labeled 2 is picked once if the balls are drawn without replacement? Now, this is going to change our answer. Okay, so let's have a look again. We're going to go 2. Let's draw our little balls again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's move a bit faster this time, shall we? 2. All right. So let's draw our tree diagram again. We're either going to have a 2 or we are not going to pick a 2. We are either going to have a 2 or we are not going to pick a 2. Beautiful. Now, probability of picking a 2 the first time we know is 1 out of 10, and this is 9 out of 10. Now, this is where it changes because this is, remember, without replacement. So if I pick my 2 here, gone, what is my chance of picking another 2? Well, there isn't any. So we actually don't need to include that. Doesn't happen. Can't happen. Okay. But if I pick a 2 the first time and without replacement, what is the probability that I pick not a 2? Well, we're not even going to include this one, so let's even just erase it. Right? Now, I don't have a 2 there, but I'll tell you what I do have. I have 9 things that are not 2 out of 9. Okay? Pretty crazy. Now, here, I have the probability. Yeah. Here, I'm not picking a 2. And maybe I'll draw my little thing back in here. Okay. So now we're looking at this section, right? Go down this way. I didn't pick a 2, so let's just tack this one off the end. In fact, let's get rid of it because I'm taking it out now. Okay. Now, let's look at the probability of choosing a 2. I have 1 out of 9. So you can see that the bottom amount changed because we reduced our sample space. The probability of choosing not a 2 now is 8 out of 9. Okay, so now we have a different set of results, right? We can either have chosen a 2 and then not a 2, or not a 2 and then a 2, or not 2 and then we've also chosen not to again. So let's have a look at what the probabilities of these are. I might even just do them in different colors, just for a bit of fun. So let's do the first one in pink. The probability of 2 and then not 2 is equal to, let's follow our diagram, 1 out of 10, and we're going to multiply that by 9 out of 9, which is 1. So 1 out of 10 multiplied by 1 is equal to 1 out of 10. Now, let's do this one. Let's go green. Probability of not 2 and then 2. Let's follow our diagram. We have probability of 9 out of 10 multiplied by 1 out of 9. Probability of 9 out of 10 multiplied the probability of 1 out of 9. Okay, is equal to 9 out of 90, which is 1 out of 10. Isn't that interesting? That is very interesting. that's just a cool little coincidence thing. Anyway, yeah, the probability of choosing not a 2 and then not a 2, okay, is 9 out of 10 multiplied by 8 out of 9 is equal to 9 times 8, 72 over 90, which would simplify down to 8 out of 10, because you can divide both by 9. Cool. Which is 1 plus 1 plus 8, which is great. Anyway, we are looking at the probability of choosing one of our 2's. So here, the last one that we calculated actually doesn't even come into it. So you can see we have a not 2 and a not 2. So let's just even cross all this out, right? But here we have a 2, and here we have a 2. Oh, which means we're going to add these two ones together. So the probability of choosing a 2 is equal to the probability of a 2, oh, and then not a 2, plus, plus the probability of choosing not a 2 and then choosing a 2, which is equal to the probability, like 1 out of 10, so we calculated, plus 1 out of 10, which is 2 out of 10. There we go. Now, I was going to do this one, but I don't actually think we necessarily need to. I will move into this one now quickly, and then we can be done with it, I reckon. So, have any more? No. Anyway, so let's look at this here. All right, I might even move here for a second. I'm just going to even fill this in, right? All I want you to know now is how to fill in fill in one of these things, how to identify our information. So this is a bit of one where, there's a lot of words, but only a few things are important. Bart is purchasing a plane ticket. He notices there are only 4 seats remaining. Okay, one of them is a window seat, and the other 3 are aisle seats. Bart purchases his first ticket. His friend Josh gets on the computer and purchases a ticket immediately after. The seats are randomly allocated. Okay, so first things first, let's fill in our Venn diagram. All right, now we're going to say this little bit here is Bart, and this part here is Josh. Okay, so what is the probability initially that Bart chooses a window seat? Okay, he's the first one that's choosing. We know there are 4 seats in total, and we know that one of them is an aisle seat. Then we know that 3 of them are, one of them is a window seat. We know 3 are aisle seats. We have 4 options. Now, if he chooses the window seat, if he goes down this path here, there are no longer any more window seats, which is why we can't see another arm of the tree diagram. So, if he chooses the window seat, that means Josh must get the aisle seat the second time around because there are only aisle seats left. So it's a 3 out of 3 chance, right? However, if Bart chooses the aisle seat first, then we know that our total is still reduced by 3, but the probability of getting window seat, it's only 1 window seat left still, so it's now 1 out of 3 chance. The probability of getting an aisle seat is a 2 out of 3 chance. Okay, so we have just done this. Find the probability of the edges of the tree, which is that. Now, what is the probability of his friend John has an aisle seat? Well, we have here and we have here. And the probability of this is 1 out of 4 times 3 out of 3, which is 1 out of 4, because 3 out of 3 is just 1. And the probability of this is 3 out of 4 times 2 out of 3, which is equal to 6 out of 12, which is a half. So the probability of these two things happening is equal to a half plus a quarter, which is a 3/4 chance. Now, what is the probability of John receiving an aisle seat if Bart has a window seat? Here, really, it's a full chance. This is looking at this is front loading a bit of conditional probability. So right now, we're saying Bart has the window seat. He has the window seat. What's the chances that he gets an aisle seat? Well, we know the window seat's not available anymore. It's only aisle seats. So the probability of this happening, of John, of the aisle seat, given the window seat was chosen first. So this is kind of the notation that we'll get into next. But this means we're looking at probably of an aisle seat happening, given this thing has happened first. Okay, and that is 1, right? So this is kind of saying we're looking from this point in the tree diagram, which is here, probability of the window seat happened. Now, what's the probability of this occurring? Well, 3 out of 3 is 1. So the probability of there is just 1. Okay, but we'll get into that more next week. But for now, that's it. Good work. Get into it. The questions that I expect from you today, I'll write them here. Okay, so in fact, the way that I want you kind of approach this is the worksheet will be handed out. It's going to be kind of on your Google Classrooms, but I just want you to work through it. So what needs to be done today is questions 1 to 5, which is part of your understanding. But I want you to continue to work down through that worksheet. So hopefully by the end of this week, we've completed everything in that. If we've done that, we're going to be in great settings for the test. Okay. Questions 1 to 5 must happen. Then just follow it on after that. Continue down after. Beautiful.